This experiment deals with dangerous and caustic materials. Proper protection and safety gear must be used. Additionally, this experiment must be carried out in a fume hood or outside. Cotton consists of about 90% cellulose. Cellulose is a sugar polymer made of D-glucose units all attached together. Most animals are unable to break down cellulose, and in humans, cellulose is largely undigested and is often consumed as dietary fiber. Cellulose is extremely versatile, and it is the most abundant organic polymer on the planet. It serves to make many things, such as paper, clothing, cellophane, and much more. However, to make these products, the cellulose must first be dissolved into a solution. Cellulose is extremely resistant to dissolution, but luckily several solvents for cellulose have been discovered. In this video, I'll be making Schweizer's reagent, which is an aqueous-based cellulose solvent. For this experiment, you'll need 5 grams of copper 2 sulfate pentahydrate, or 3.2 grams of anhydrous copper 2 sulfate. You will also need 1.6 grams of sodium hydroxide and about 100 milliliters of ammonium hydroxide. About 2 grams of cotton is required, or you can use another source of cellulose such as toilet paper. A 10% acid solution of nitric acid, sulfuric acid, or hydrochloric acid is required, but the experiment seems to work best with sulfuric acid. First, add about 5 grams of copper sulfate pentahydrate to about 500 milliliters of water. I only had copper sulfate pentahydrate available, however, you can use anhydrous copper sulfate instead. If instead you have anhydrous copper sulfate available, simply dissolve 3.2 grams instead of 5. The anhydrous copper sulfate is significantly more soluble in water, and a lot less water is needed. Stir the copper sulfate until it is all completely dissolved into the water. In the meantime, dissolve about 1.6 grams of sodium hydroxide into about 10 or 15 milliliters of water. The dissolution of the sodium hydroxide is quite exothermic, and the water will heat up a little bit. Once all the sodium hydroxide has dissolved in the solution, it should be no hotter than warm to the touch. If the solution feels anything more than slightly warm, you'll need to cool it down in an ice bath before continuing to the next step. The copper hydroxide that we want to produce is extremely sensitive to heat. It can decompose to copper oxide at temperatures as low as 60 C. Cooling before the next step likely isn't necessary at all unless for some reason you decide to use less than 10 milliliters of water. Next, decant the sodium hydroxide solution into the copper sulfate solution. Immediately, a nice blue copper hydroxide precipitate should form. I washed the sodium hydroxide beaker with a small amount of water and added it to the solution. Next, mix the two solutions thoroughly. This serves to react as much sodium hydroxide as possible with the copper sulfate. This reaction is a double displacement reaction, and the overall reaction can be seen above. In the solution, the copper sulfate and the sodium hydroxide are split up into their respective ions. All the ions are floating around in solution, and this allows for the copper ions to recombine with the hydroxide ions. This forms the insoluble copper hydroxide solid, which precipitates out of solution. This is another replicate of the reaction between the sodium hydroxide and the copper sulfate. I'm including this replicate to show that the colors are not always consistent. This one produced a darker blue, while the previous one produced a lighter baby blue color. I let the precipitate settle for about an hour. In my case, the precipitate was a light baby blue, but don't be alarmed if your precipitate is dark blue or green. Then, decant off the top layer, which contains mostly sodium sulfate. This next step is optional and likely completely unnecessary, but you can do it if you like. If you would like to wash your copper hydroxide, add a few hundred milliliters of water, and then stir it for several minutes. After several minutes of stirring, let the solution stand and let the precipitate settle to the bottom. The precipitate will take at least an hour to settle to the bottom. Once the precipitate has settled, decant off the water. I decided to carry out this entire procedure without using gravity or vacuum filtration. If the copper hydroxide is allowed to completely dry, it will cake onto the filter paper and be a pain to remove. However, if it is left wet, it becomes a viscous goop. It is a pain to scoop up and remove from the filter paper, and there is always an inevitable loss of copper hydroxide in the filter paper. I found it much cleaner and easier to simply leave it in the beaker and let the precipitate settle. However, filtering is much more time efficient. Next, add 50 milliliters of 29% ammonium hydroxide to the copper hydroxide. Immediately upon addition, the solution should become a very dark black-purple color. This is due to the formation of a complex between the copper hydroxide and the ammonium hydroxide. The reaction is shown above. The final complex is called tetraamine diaqua copper dihydroxide. This final complex is what associates with the cellulose and allows it to be dissolved into solution. After all the copper hydroxide had dissolved, I added another 50 milliliters of ammonium hydroxide. After this final addition of ammonium hydroxide, the Schweizer's reagent is ready. Now to test the solution, we add some cotton and see if it dissolves. It does not dissolve cellulose as easy as adding sugar to water, but nonetheless it dissolves cellulose quite well. I simply kept adding cotton until the rate of dissolution slowed down, as this told me it was getting near saturation. This is quite impressive, as only about 3.2 grams of anhydrous copper sulfate would be required to do this. This solution is actually from a separate replicate. I'm including it to show you that the colors are not always consistent. You do not need to worry as long as the color of your reagent is on the range between dark blue-purple to black. After completing this experiment several times, I found that the colors of the solutions were quite variable, but each time the reagent worked just as well. After a while, you'll notice that the solution becomes quite viscous and the cotton has a hard time dissolving and getting wet by the solution. This should tell you that the solution is getting close to the saturation point. Do not add too much cotton, as we don't want there to be undissolved cotton fibers floating around in solution. Here we can see that the solution has become quite viscous. Next, I pipette out some of the solution. I drip some of the solution back into the beaker to show you that it is truly a dissolved cellulose solution and not merely cotton fibers in suspension. Next, I slowly pipette out some of the cellulose solution into a 10% sulfuric acid solution. Immediately, the previously soluble cellulose becomes insoluble. This is because the sulfuric acid destroys the complex created by the copper hydroxide and the ammonium hydroxide. Next, I poured in a lot of the dissolved cellulose into the sulfuric acid solution to have it precipitate. You can see that it precipitates immediately upon addition, but it maintains its dark blue color. This is due to some of the Schweizer reagent still associated with the cotton. Upon thorough mixing, the dark blue color of the Schweizer reagent disappears. Eventually, the cotton becomes completely white and the solution takes on a very slight blue color. The sulfuric acid reacts with the ammonia hydroxide and the copper hydroxide according to the reactions shown above. The reaction between ammonium hydroxide and the sulfuric acid produces ammonium sulfate, which is colorless when dissolved in solution. However, when copper hydroxide reacts with sulfuric acid, it produces copper sulfate, which is a blue color in solution like you saw earlier in the video. Next, I added some of the solution to a 10% hydrochloric acid solution. Like the sulfuric acid solution, the cellulose precipitates immediately. When mixed thoroughly, the blue color of the reagent also disappears, however the solution takes on a light green color instead. This is due to the formation of copper chloride as shown in the reaction above. The hydrochloric acid reacts with the copper hydroxide to form the copper chloride salt, which is green when dissolved in solution. Finally, I added the remainder of the cellulose solution to about a 15% nitric acid solution. This portion of the cellulose solution was much more concentrated. As a result, the cellulose precipitate was much thicker than when added to hydrochloric acid and sulfuric acid. Next, I vigorously mixed it to neutralize as much reagent as possible. The solution was very close to the top of the beaker, so inevitably some splashing did occur. Eventually, most of the Schweizer reagent was neutralized. Like the sulfuric acid solution, the solution slowly took on a faint blue color. This is due to the formation of copper nitrate as shown in the reaction above. Like with the other acids, the nitric acid reacts with the copper hydroxide to form its corresponding salt. Like copper sulfate, copper nitrate is blue when dissolved in solution. And as you can see, there was a lot of cellulose that was dissolved in the solution. The nitric acid cellulose solution was then transferred back to the original Schweizer reagent containing beaker. More Schweizer reagent was neutralized, and as a result, the blue color became much more evident. In total, about 2 grams of cotton was dissolved, which amounts to about as much as shown here.